Hello, my name is Corey, and I'm doing my presentation on securing processors against insider attacks. Because of the focusing issue, I'll stay out of the scene and you can watch the slides. Some background upon this is the hardware has been historically assumed free malicious events. Software Trojans have been the main focus, but now, because of outsourced alternatives, have been gradually replacing in-house alternatives for hardware development. This has become an issue. Why has it been outsourced? Because of cost and money and time. So a standard is needed, a standard for hardware production and testing. So not only do you have to test for production environment, but you also need to have a reliable testing team to make sure that there are no malicious activity or Trojans present on your device. Primary concerns for this are pretty straightforward: intellectual theft, the military DoD purposes with denial of service events, or randomly shutting down or exploding a rocket. That could be pretty bad. And of course, the leakage of personal information. So there needs to be a plan for inevitable dependence on those third parties. This outline of this paper, it was summarized by the Trojan assertion detection techniques, the difficulties for the detection, security modules and their attacks, and preventing detecting attacks. And of course, I'll go over the experimental preparation, outcome, related works, future works, and the conclusion. This is the processor design flow. You'll notice on the left there is the reference to a rogue designer and a design team, and a rogue element and the fabrication team, which could physically invite or implement Trojans at the hardware level, whereas the design team, rogue Trojan or rogue designer, can implement or design rogue elements within that device. So those are the insertion techniques at both the design and foundry level. So what about detection? Well, there's the RTL verification, which is the register transfer level net list that's created, and of course the layout verification itself. On the foundry level, there's side channel characterization, which enables path delay and power consumption benchmarking at the gate level, and side channel measurements. What are some difficulties in detection? Well, at the design house level, for the layout verification, you really do need a Trojan fee or golden design to compare it to. This is difficult. And then also at the RTL verification level, and not only is it difficult to do, but it's also very time consuming. This is not feasible whenever you're trying to do some kind of RTL verification for millions of chips. At the foundry level, there's inter and intra-die variations. There's also measurement errors in aging of the chip. So a paper had done research showing that if the Trojan was below a certain percentage, say 1 to 3% of the total die size, then it would not be able to be detected by the foundry level testing. So if you were able to force the Trojan above 3%, then it would be detected regardless. Whereas if it was below that 3% or 1% line, then it would have that chance of not being detected, and I'll talk about that later. So in countering this, some security modules were developed, and of course the vulnerabilities were exploited against those security modules. And I'll be using this diagram to assist in explaining where those security modules and vulnerable exploits exist. First one is data instruction encryption. So in binary, you do a hash of the non-malicious instruction, and you compare that to an instruction coming through the pipe, and then you compare it. Any kind of mismatch will trigger a flag. But then on the vulnerability side, you can bypass this with a simple OR gate. So you'll notice here, instruction sent, there's a mismatch, so you send a 0. Well, you OR with a 1, anything OR to the 1 is a 1, and you load it. The second one is the secure random address stack, or the SRAS, which compares the sent address to an address saved in memory. And upon a mismatch, an interrupt is triggered. Well, you can exploit that vulnerability by bypassing the SRAS with just a flag. So if the Trojan sees that flag, it resets the signal with an AND, and you'll see that here. SRAS checks, sends a 0, 0 and a 0 is a 1, sends back. Next one's the randomizer matching de-randomizer. Of course, just bypass that with a randomizer, de-randomizer. So what is that? Randomizer will randomize an instruction, send on the pipe. De-randomizer matches the randomizer, and will de-randomize that instruction. Well, if a Trojan is along that pipe and maliciously activates something to change some of that instructions, de-randomizer will de-randomize garbage, and that instruction will not be committed. So, like I said, you can bypass that, go back to this, and you load that OR gate with whatever is 0, or to the 1 becomes a 1. Next thing is an integrity check with a commit flag. So you check the integrity of that instruction with some logic, and then upon any kind of activity being detected, we'll set a flag. Well, the vulnerability, of course, setting that commit flag regardless of an attack. So you'll see that here. The GTPM, I'll explain what that is in a little bit, gets ORed with a 1 and then is committed, regardless of any malicious activity being detected. Next thing is an instruction checker. You compare instructions from the pipeline with instructions that were fetched from memory. Any kind of mismatch, you'll trigger a flag. Same idea as before, you force a load signal to execute erroneous instructions regardless of any activity being accessed. You'll check that here. Instruction checker goes down the line. If it detects a 0, hands it with a 0, sends it over. 0 and a 0 is a 1, so it continues to load that information. Final one is a TrustNet Data Watch, which is a really great tool. It monitors microarchitectural events. The fault with that is, despite it being able to detect these events and trigger a flag, you can still force the match signal with an OR. So, similar to before, you match, detects, sends a 0, you OR with a 1, still a 1, and then you continue with the instruction anyway. So, what are some methods for preventing and detecting these attacks? Well, they've noticed that these are the vulnerabilities, and they wanted to do something better. So, they looked at doing some kind of module encryption with a key. Remember I talked earlier about having the key larger than a certain percent of the die size. So if the Trojan was larger than, say, 1%, there's a likely percentage or likely chance that that Trojan will be detected rather than it being something small like 2 gates or 10 gates in size. So you store this key within the security module. And upon detection, no key is then sent. So after execution, the security module encrypts the processor and the invalid key is sent to the Dcache controller. So here's an example. You have the rogue element in the design team. The logic or the trusted security team encrypts the logic. So you have the locks represented by the dark shaded ones. The unlocked checked here. So it comes to here, they check for Trojans. Upon success, they lock it again, send it to fabrication. They develop the IC. Comes over to here, they unlock the IC, check for Trojans, and upon success, they send out for deployment. So pretty simple. Here's a comparison of before and after. Before, straightforward. We talked about this a little bit. Afterwards, you have the untrusted regime, trusted regimes, untrusted and trusted. You'll notice some added elements such as the logic encryption, which is where the key is implemented and added. They're locked, unlocked. Before, it just sends all straight through. So say if I design rogue elements here, it's too small for a fabrication area to be detected, it sends on through. But here, if a key is larger than, say, 1% of the die size, the Trojan then needs to be the size of the key plus its actual malicious intent. So that forces it to be larger than that 1% detection size. So, thus, after it cuts through here, the IC testing and detection will inevitably detect any Trojans. So how did they experiment on this? They had a great idea, and they have a great implementation plan. But how did they experiment? Well, they used Simple Scalar, which is a hardware benchmarking tool, very common. And they performed benchmarks with DTPM and SRES security modules. So what are those? I mentioned those before. The DTPM is the Dynamic On-Chip Trusted Platform Module. SRES is the Secure Return Address Stack. So what do these do? These provide built-in dynamic protection against return address tampering. So they benchmarked with these tools, and they also benchmarked using processor encryption, and I'll show that in a second. What did they benchmark on? They benchmarked against common libraries such as bzip2 and GCC. So notice here that these are the benchmark libraries, bzip2, GCC, and the others. And this is the performance impact on a chip. And you'll notice that the 2 on the left are the DTPM, 2 on the right, SRES. You'll notice that even though DTPM has a larger impact upon processor performance, there's little implication or little impact with the addition of processor encryption. Whereas SRES, there's a significantly greater impact on performance with the addition of processor encryption. So why is DTPM much larger? Well, DTPM they have said that checks every single block, whereas the SRAS only checks the return instructions. So, something to consider. Even in here, the stream, they didn't mention specifically why, but you'll notice with the addition of the processor encryption, it's comparable with processor encryption on DTPM. So, there is a significant impact on performance, and they also mentioned that there's a comparable impact upon power consumption. Working on related works, talk about logic encryption, which is on the design level. You talk about hiding functionality by adding a bunch of extra gates, which is a type of obfuscation on the hardware level. So it hides that intent through multiple gates or the addition of hundreds of gates. So you produce correct outputs only on correctly applying the valid key. So you mentioned here the key. One is the key with an XOR gate. So upon comparison, if it comes out true, instructions are then sent down the pipe. So what are some future works on the work from before? So I mentioned before that there was a significant impact upon performance and power consumption. So you need to specifically target the decreased power consumption because you may have the most secure phone in the world, but if you have no battery life, no consumer will want to buy it. And then what about the decreased performance impact? Well, DTPM checks every block, and SRES checks every return instructions. What about sporadic testing and checking? I'm not sure what the answer would be, because I know sporadic checking would allow the possibility of malicious activity being sent through, but that's something that needs to be considered. In conclusion, detection, mitigation, and protection techniques for each hardware Trojan type has been done, and that's great. And there seems to be proactive activity being done for a great defense. It shows that best defense is a good offense. And I think that's great. They need to do that. They can't wait for something to happen. They need to be prepared for it. And I think the biggest conclusion of all is, despite the overhead to the key-based approach, it's been proven superior in making it difficult for Trojan assertion at design and fabrication phases. Thank you. Just in time.